Radioactivity is a natural component of the environment. This is not something that man has done to the Earth by trying to build nuclear power plants or anything. Radioactivity is natural. Living organisms have adapted to survive exposure to normal radioactivity. Where does the radioactivity come from? Well, some of it comes from space. Wearing a tinfoil hat is not going to protect you from it. But some of it gets through the atmosphere. Our atmosphere does block a lot of the radiation from space. But we also have radioactive substances in the ground. Any of the atoms that have atomic number past 83, 83 is bismuth, anything past that is radioactive. And when you look at the periodic table over here, you find bismuth. Bismuth has a mass, an atomic mass of 208.980, and the next one over, polonium number 84, its mass is 209, a whole number in parentheses. And everyone after that, the mass has a whole number in parentheses. Well, except for 3 of them there, but most of them. Those are all radioactive. So if it's got the number in parentheses like that, those are radioactive. There are some elements with mass numbers less than 83 that are radioactive, but it's mostly those that are above. Radioactive nuclides decay at different rates. Some of them decay very quickly, some of them decay extremely slowly. And so, of course, we need to quantify that. We quantify that with something called half-life. And this is used in other applications as well. Like you talk about a certain drug is going to have a half-life. It's the same concept. Half-life is the time it takes for half of the parent nuclides in the radioactive sample to decay to daughter nuclides. In terms of a medication, it's the time it takes for half of the medicine to be metabolized by your body. So a radioactive sample does not decay to 0 atoms in 2 half-lives. In the first half-life, half of what's there decays. In the second half-life, half of what remains decays. So it's cutting in half with every half-life. So after 1 half-life, you've got half left. After 2 half-lives, you have a quarter of what you started with. After 3 half-lives, you have 1/8. Because you're cutting things in half. You start with 1, and then it goes to 1/2, and then you cut that in half, you get a 1/4. You cut that in half, you get an 1/8. You cut that in half, you get a 1/16. You get the idea? Just cut it in half every time. So each of these arrows would represent 1 half-life. So this is 1, 2, 3. After 4 half-lives, you have 1/16 left. If the half-life is very short, that means that nuclide decays very quickly, and we say it's very active. It's got a lot of decay events per unit time. It's going to emit a lot of radiation in a short period of time. A decay event is just an emission of radiation by a single nuclide, a single atom. Radon-220 has a half-life of approximately 1 minute. So if you started with 1,000,000 radon-220 atoms, after a minute you'd have 500,000. After another minute, a total of 2 minutes, you'd have 250,000. After another minute, you'd have 1/8 of a million. So radon's very active. Thorium-232 is much less active. It's got a half-life of 14 billion years. So it has many, many fewer decay events per unit time. So if you started with 1,000,000 thorium atoms, thorium-232, it would take 14 billion years for it to decay down to 500,000. So we can see this illustrated here. If you're starting with 1,000,000, and here you've got a 14 billion year half-life. After 14 billion years, you're down to half. After another 14 billion, you're down to 2.5 million, and then 1.25, and then whatever half of that is. Yeah.
I don't know much about the time and so on. Where did it come from? Where did it come from?
Okay, so we have a section on bombs. Okay, so we'll get to that. Yeah. Each nuclide has its own half-life. And the half-life of a radioactive nuclide is not affected by physical conditions or the chemical environment or anything. It is intrinsic to that nucleus. Because the nucleus is just, it's a little bit like a time bomb. And it's just sort of ticking away, and it's going to decay when it decays, and there's nothing you can do to stop it. Sticking it in the refrigerator is not going to slow it down. Heating it up won't make it go faster. There's nothing you can do. It just decays. Just as an example, I would not expect you to memorize these. Thorium-232, we've talked about that. 14 billion year half-life, that decays by alpha decay. Uranium-238, also a very long half-life, also alpha decay. Carbon-14 is beta decay, has a half-life of 5,730 years. We'll talk about that one in a minute. Here's radon, 55.6 seconds, about a minute. That's also alpha decay. The type of decay does not indicate whether it's got a long half-life or not. And then thorium-219 has a really, really short half-life, a microsecond. So in a microsecond, half of it's gone. In another microsecond, half of what's left is gone. So half-life varies tremendously. There are more complicated ways involving math equations to talk about half-lives and how much stuff is left. We're going to keep it really simple. We're just going to be talking about cutting things in half. Okay? So a radium-226 sample initially contains 0.112 moles. How much radium-226 is left in the sample after 6,400 years? The half-life is 1,600 years. So what we would like to know is how many half-lives is 6,400 years? Well, you can do that a more picture way, more of an intuitive way, or you can do some math. The math way would be to take the total time here and divide by the half-life and find out how many half-lives is that. But you can also just start drawing, essentially. So I started with 0.112 moles. And after 1,600 years, because that's what it tells me the half-life is, after 1,600 years, I have half of that left. Well, what's half of that? I don't know. Get your calculator out. 0.112 divided by 2. So 0.056. Well, after another 1,600 years, divide it in 2 again. So 0.056 divided by 2. 0.028. So keep track of the time here. So at this point, 1,600 years, 1,600 years have passed. And then another 1,600 years, so this makes 3,200 years, right? So let's do it again, another 1,600. So 0.028 divided by 2, 0.014. So now we've got 32 plus 1,600, so 4,800 years. We're getting closer. divide it in 2 again. So 0.007 moles. And we're adding another 1,600 years. Now we're up to 6,400. That's the time period we wanted. So the answer is 0.007 moles of that are left after 6,400 years. Yes?
Question about six.
Okay.
So, do we just leave it at 0.007 even though we started with pretty significant figures?
That's an excellent question. Technically, it should probably be 0.00700 moles. But we won't try to trick you with this sig figs. Any other questions? So these naturally occurring radioactive elements, they either have very long half-lives, they've been here for billions of years, and they're decaying away, but it's happening so slowly that they're still around. Or if they've got a short half-life, they must be being formed by something else. Because as one thing decays, it forms other things, and some of those things are radioactive. Uranium is the largest, the heaviest naturally occurring element. That's number 92. On the periodic table, you'll see that all of the elements after 92 have their symbols in white. They're just an outline. Those are all man-made elements. Uranium-238 is the heaviest one that actually just occurs naturally. So uranium-238 decays to thorium-234. It has a half-life of 4.47 billion years. And then thorium-234 is radioactive. It decays to protactinium-234. That has a half-life, the 234, of about 24 days. So the thorium-234 is decaying almost as it's being formed, right? It takes a long time to form it, and then once it's formed, it decays fairly quickly. That makes, protactinium, Pa. That's also radioactive, decays to uranium-234. That half-life is 244,500 years. The process continues. It goes from one thing to another, sometimes going up, sometimes going down in mass. Eventually, it gets to lead-206, which is stable. Along the way, it produces radon gas, which is radioactive and dangerous. So what's happening is that all of the uranium-238 present in the environment is slowly decaying to lead-206. There's nothing we can do about it. It's just happening. You might think it's good, you might think it's bad, doesn't matter, it is. All of the nuclides in this series are present in the environment. Their amounts are going to vary depending on their half-lives. If it has a short half-life, it's going to disappear very quickly. If it has a long half-life, it's going to hang around and there'll be more of it around. So this is a graph, and this is, just for your general background knowledge. This is a graph of what happens. So uranium, the heaviest naturally occurring element, it decays to thorium-234, decays to protactinium-234, then to uranium-234, then to these guys. What we have here is mass number versus atomic number. And so they get smaller, and then it does a bunch of back and forth stuff over here, and eventually stops it at lead-206. Lead-206 is not radioactive. Once it becomes lead-206, it just stays that.
So does that mean bismuth be radioactive?
Yeah, bismuth, there are radioactive forms of bismuth, yeah. But some of these elements have no non-radioactive isotopes. All the isotopes are radioactive.